So this is actually the last section in this chapter. We'll break it up into a few videos, but it's about percent composition and chemical formulas. So this is going to answer a question that we haven't really talked about yet, which is how do we know? How do we know that water is 2 hydrogen and 1 oxygen? How do we know that salt is 1 sodium for every 1 chlorine? We can't see the atoms, right? So how do we know this? And that's a good question. And one of the ways is that we've been able to figure out things like percent composition. And from percent composition, we can find what is going to be called empirical formulas and then the actual molecular formula. So percent composition is actually something that we have talked about earlier this year. Percent composition, if you don't remember this definition, write it down. It's the percent by mass of each element in a compound. And so you have here 2 pie charts that are showing you the percent compositions of potassium chromate and potassium dichromate. Chromate and dichromate are 2 polyatomic ions that are on your sheet, but they weren't one of the 9 that I had you memorize, so you may be a bit unfamiliar with those. But you can see that even though they're both of these compounds are made from potassium and chromium and oxygen, they are made of those elements in different proportions. They have different percentages of potassium and chromium and oxygen, and therefore they have different formulas, and therefore they have different properties. So how can we solve for percent composition? So this is the way that we did it back at the beginning of the year. I would give you the data, and you would just need to plug it into this formula, that the percent by mass or the percent composition, those 2 things are the same thing, of a compound. Oh, this should be compound. The percent composition of a compound is equal to the mass of the element that we're talking about over the mass of the whole compound. And in the beginning of the year, when I gave this to you, I would give you the mass of the element and the mass of the compound. So an example like this, when 13.6 gram sample of a compound containing only magnesium oxygen is decomposed, 5.40 grams of oxygen is obtained. What is the percent composition of this compound? So when it asks for the percent composition, it's going to want 2 things. I want to know the percent oxygen, and I want to know the percent magnesium. Okay, so apply the formula to this. I would want to know the mass of the oxygen over the mass of the whole compound. And then, of course, I would need to multiply by 100% to get the decimal into the percentage of, in this case, oxygen in this compound. The mass of the oxygen is given to me in the problem as 5.40 grams. The mass of the compound is 13.60 grams. And look at what happens to the units, right? A gram in the numerator and a gram in the denominator cancel out. Therefore, the only unit in my answer is actually just the percent sign. It's not really a unit. It just tells you what type of number it is. And I divide those 2 numbers, and then I multiply by 100%. And I get 39.7%. Still, significant figures, yep. They're definitely applying here. In the next problem, so to find the percent magnesium, so I'm going to need to know the mass of the magnesium and the mass of the compound. And of course, yes, I do know the mass of the compound. That is still the same, 13.60 grams. How do I find the mass of the magnesium? Well, I know the mass of the compound and I know the mass of the oxygen, and this problem tells me it only contains these 2 elements. So I just subtract those 2. And I get the mass of the magnesium to be 8.20 grams. And then I, of course, divide those, multiply by 100%, and I get 60.3%. And when I look at these 2, these are the only 2 elements in the compound. These percent composition should add up to 100, and they do. So that means I'm probably on the right track. Now, what is the new thing that we are doing this year is the percent composition, in this case of like manganese to nitrate, without any data. The only data that I'm going to use is the data from the periodic table. Because on the periodic table, I can figure out what the mass of 1 mole of this compound is by adding up all the molar masses of the elements. And then I can find what the mass of 1 mole of manganese, 2 moles of nitrogen, and 6 moles of oxygen. So I'm going to be using those molar masses from the periodic table and basically the same formula. So if I want to know the percent manganese, I of course am going to need to know the mass of the manganese over the mass of the compound. And so I look on the periodic table. In this problem, there's 1 manganese. So the top is just the mass of 1 manganese. The denominator of this fraction will be the molar mass of this manganese 2 nitrate. So I'm going to add up 1 manganese, 2 nitrogen, and 6 oxygen. So it's going to be a big number. It comes out to be 178.96 grams. And so when I do this out, divide those two, multiply by 100, the numbers are coming just from the periodic table, which means that they all have 4 significant figures. So my answer here is 30.70% manganese. Now, if I want to know the percent composition of this compound, I need to know everything. So the percent of nitrogen, let's do that next. So what will that have to be? Well, of course, the mass of the nitrogen over the mass of the whole compound. Now, the mass of the nitrogen is the mass of the 2 nitrogen that are in there. So don't forget that. That's a common mistake. So, of course, it's going to be 28.02 grams of nitrogen and 178.96 grams of the whole compound. So once you figure that out once, it's nice you can just use it for the next few problems. And this will equal 15.66% nitrogen. And then the last one is the percent oxygen. And I will need to know the mass of the oxygen over the mass of the whole compound. And the mass of the oxygen, the mass of the oxygen, there's 6 oxygen, right? 2 times 3 is 6. So 6 times 16 is 96 grams of oxygen, and the 178.96 grams is the total of the compound. And multiplied, and then 96 divided by 178 times 100% equals 53.64% oxygen. And students will often ask, like, do I need to even do that last one? Can't I just subtract from 100? And no, theoretically you should be able to do that. But if you have done the first part wrong, then you will never catch your mistake and you will get this whole problem wrong. So if I had done this and added them up at the end, so if I add these 3 up, it comes very close to 100%. Sometimes it won't be exactly 100% because of rounding errors and such, but these will come out to be very close to 100%. That means I've done the problem correctly. If I have not done the problem correctly, these may not come out to total 100%, but that's great because on a testing situation, then you go back and you go, oh, let me see what I did wrong. Maybe you found the molar mass of the compound wrong. Oftentimes what people do is they don't actually, they write just 1 nitrogen up top, not 2. So those are all things that we can look for. So I would say to do them all individually and then add them up, and it should equal 100% at the end.